Thanks for the introduction. I work on machine translation, so you might take some parallel corpus of Chinese and English and pass it through this curious automatic analyzer machine I found in Beijing. And maybe it will translate some Chinese into other prohibitions about parks in Beijing. Now, in the Hall of Mental Cultivation, that process becomes not really scalable. We need more data, and just photographing Beijing tourist signs isn't enough to actually train a reasonable system. So our field has gone to bureaucrats, and this is the statue in Iceland of the unknown bureaucrat. Nice blockhead in a suitcase and all that. And we harvest their data because often in Europe at least, they translate a lot of data just to talk to each other. So there's still a problem with that because the EU is trying to expand their translation service, which was trained on bureaucratic text, to online dispute resolution. And when someone complains that their chair broke, it translates as le président, not la chaise, because it's used to bureaucratic text and it's the chair of the committee, that sort of thing going on. How do we fix that? Well, there's one project that we're mining the web for translations, and this is what we've branded as Paracrawl. You can go to our website and download parallel corpora that we've got from there already. Sorry, there's no Ukrainian. It's funded by the European Union. And we still have the other side, that's the automatic analyzer. There's a lot of open source tools that exist out there, Marian and Tensor to Tensor and FairSeek and OpenNMT, that people can train their own translation systems on. And actually the community has been quite good about doing open source software for translation, even the large companies that are traditionally based on closed source software. But we wanted to make this even closer to the users. And the idea in the Bergamot project is to actually bring translation client side to the user. And the reason for this is it preserves privacy. Rather than go into an online service where you might have your HR documents or something under a non-disclosure agreement, you can run it client side directly on your machine. And our project website is there. We haven't launched a public thing yet, but we're working on it, and you can follow us on that site. I really like Malta, by the way, because they have the .mt domain for machine translation. So these projects actually relate to each other in a way. The Paracrawl project produces data, but as we'll see later in the talk, we also take fast translation that's necessary to run on a desktop and feed that back into producing more parallel corpora. And that's sort of the outline for this talk. Part one is how do we get the data, and part two is how do we bring it to the users. So moving on to the Paracrawl project, and this is actually a consortium of universities and companies that I put on the slide here. We're doing all 26 EU languages plus Icelandic and Norwegian. These are formally what's part of the Connecting Europe facility, which is slightly different from Horizon 2020 with the subtle distinction that Ukraine is not part of the Connecting Europe facility, so that's why we're not funded to do Ukrainian, for instance. We're also doing Spanish co-official languages. These are the ones that you're allowed to address officialdom in those languages in Spain, and they have to deal with you in court cases and such. We've collected for each of those languages between, depending on the language heavily, 4 million to 1 billion words of translated text from the web. And I'm counting in English when I say that, just to be consistent in terms of what is a word, from 500,000 websites. And this is largely before we've finished downloading a petabyte from the Internet Archive to vastly expand our data collection, and I'm hoping we'll produce a lot more data. And we're processing that now. We've done part of it in a release, but there's more data coming. So here's the size of the parallel corpora that we've produced for various languages, all measured in terms of English words. That really seems to be the only way to measure consistently. And you can see the usual suspects of French, German, Spanish, Italian are very high resource languages. There's a lot of translated text for them. And then Maltese, despite speaking English and Maltese there, they don't seem to have much data. Partly it's a smaller population, and also there's a phenomenon that happens to a lot of low resource languages like Hindi, where people who are online and speak Hindi and English tend to only speak English online. So you don't actually collect that much Hindi-English parallel data on the internet. Not that Hindi is one of our languages in this case, but I suspect a similar thing is happening to Maltese. And we measured the improvement that you get in terms of quality on, these are selected language pairs, going in and out of English, both from our first release, which was somewhat messy, to release 4, which is actually one old right now, but these are the most recent numbers I had. And blue is our measure of quality gains in machine translation. And the saying goes that 1 blue point is publishable. So if you improve your model and you get 1 blue point gain, you're allowed to have a paper in ACL, and if your model is awesome. But across several languages, Finnish, Latvian, Romanian, and such, and covering a range of low resource and high resource languages, we see gains in the quality. The one weird one is English to Czech, and the reason for that is largely the Czechs have put a lot of work into getting books and corpora from their books at Charles University in Prague. So they already have a strangely large amount of data for Czech, more than you would expect from just the usage and population. The pipeline looks like this complicated thing. We start at the top with Common Crawl, and we're moving to Internet Archive as a source of raw data crawled from the web. We run some pipeline to throw out the HTML, convert everything to UTF-8, normalize the text. There's a lot of messy stuff on the internet. We're also adding PDF extraction because while there aren't that many PDFs relative to HTML, we think that there's higher quality translations likely to be in PDFs, that bureaucratic organizations tend to produce that sort of text that might be in a long report. But we found that actually Common Crawl isn't deep enough. We'll talk more about that later. So we also run our own targeted crawls, and there's this loop of identifying things that we think will have more data. We pass it through language detection. Currently, that's powered by CLD3 from Google. And I'll talk about some fun issues with that later. Then somehow, once we've got all this text in various languages, we want to find what are the translations in this. And this is a huge information retrieval problem in a sense, but it's also a modeling problem that you have to think about how you're actually going to model that. And then it's really messy, and even after cleaning, it's still messy. But that's what we deliver to the website and to the EU, which is, in a sense, our customer on this grant. So we are actually feeding this data. The EU has said they are using our data to train their systems that help bureaucrats translate, and presumably will help people in the EU file disputes about their chair breaking. So I talked about Common Crawl, and we checked a statistic on how many of our translations were actually pages that existed just in Common Crawl, and only 5% are in Common Crawl. The other 95% came from crawling that we did directly. And the reason for this is some sites are really big and have a lot of data. A canonical example is the United Nations has a lot of translated text on its website. So there's specific people crawling the United Nations, and actually the United Nations released their corpora, which was quite a good bureaucratic effort inside the UN. But there are plenty of organizations that have large websites and are multilingual, and they have big websites. Common Crawl, though, is too shallow. They effectively, through their crawl rate limits and their monthly release cycle, have a cap on the number of pages per domain that they can crawl, and that's based on robots.txt and all that fun. But if you crawl for longer than a month, for instance, you can gather more data from a particular web domain. So we go into the data from Common Crawl and run a somewhat simple heuristic. If we want Czech English parallel corpora, we find websites that have a lot of Czech and that have a lot of English. That's a pretty dumb heuristic, and there are some problems I'll get into with that. But also, we're aiming to improve this just by downloading a heck of a lot more data. The Internet Archive has at least 17 petabytes of compressed web pages. That's after compression. And currently, I can only afford to get a petabyte of it because that's the budget that I have to buy hard drives. So another idea that's fancier than that, which is more experimental and I don't have results to show you yet, is can we actually learn something about a page before we crawl it, so we really only know the URL and what the links were to it, that helps us decide, will this page, if we crawl it, have a translation on it? And this is, in a sense, an interesting case of the bandit learning problem, where you only get the reward if you found both sides of the translation. So normal bandit learning, you get the reward immediately after taking the action. In this case, there's that weird delay effect. And Hugh Hang is working on that. He was at Edinburgh, and he's now at Microsoft. So I earlier commented about our heuristic about just looking for websites that have lots of content in languages we care about, but WordPress.com has a lot of content in various languages because they host people's blogs, but not much of it is translated. And actually, it was big enough that we just added a rule saying we're not going to crawl WordPress.com. It probably won't have a lot of translations in proportion to it. Kind of dumb, but in principle, something that the system could learn at a much larger scale. And honestly, this is more a performance optimization more than anything else. We also have trouble with language classification. So with apologies to the South Africans, I'm going to mispronounce one of your official languages. We crawled isiXhosa. It has a click. I can't do clicks, but anyway, we were trying to build a translation system between English and isiXhosa for medical doctors to use to speak to their patients was the end task, and we partnered with the University of Cape Town on this, and we wanted to crawl the web for anything that might be in this language. Even monolingual data would have been helpful. Problem is, that's the fraction of the time, 0.000 something, that Xhosa appears on the web relative to English. And that number is lower than the classifier's false positive rate. So just like medical testing, when there's a rare medical condition and most of the positives on the test are actually false, we have the same problem with that. And we looked at the data that was coming out, and there's some site where you trade baseball statistics in a particular format, and that was all getting misclassified as Xhosa for I don't know why, but that means sometimes you have to do things like go out to Wikipedia or an ideally clean source of data that is in the language you care about, train a language model, build your own language classifier, and just map over the internet and threshold against that language model. For these really low resource languages, that's a problem. At the same time, you want to grab as much data as you can for a low resource language. Almost any data will help. So going out to the web, if you can find it, is helpful for this. And But we were using like garbage collection leaflets from the city of Cape Town because they're translated, adding that to the parallel corpora, emailing linguists and finding out that a lot of linguists like to hold on to their data so they can publish on it, which was interesting. And some of them were actually happy to share with us. So now we have like GNOME manuals. Well, GNOME and KDE localization you can get online for free. We had some projects that from Stellenbosch University did Navy translations, and we were trying to do medical translations. So every time the doctor would say something in COSA, it was advising them to like check their hard drive or diagnose some computer condition because that was the data we had to train this system on. And we actually ended up paying people to do English to COSA translations in domain for us so we could get a less terrible system. So how do we match all the text once we've hopefully got it in the right language? And actually we still have like a 4% problem with the wrong language. There's been a lot of work on this. So the early work that is fast but doesn't necessarily find all the data is you look for language codes in the URL and hope that there's a lang equals en, lang equals is, and then you have Icelandic English parallel corpora. Google decided in 2010 that they were going to translate everything on the internet into English and then use that to match data. Not necessarily everything, but a large collection of their web crawl. And more recently from Facebook, there's been this idea that you take a sentence, run it through a neural network, and convert it into a vector. And it's largely just a machine translation system, but constraining the vector that goes between them to be the only way you can communicate from the source language to the target language, and that produces some notion of a multilingual vector. We're actually working on a paper that's technically in the anonymity period that will compete with that. So I'm not going to talk about our work on neural network vectors, but you can see translating to English and matching, which is what our current pipeline is. From an information retrieval perspective, it's somewhat boring. From a fast translation system perspective, this costs a lot of time. We translate everything we can to English, which implies, by the way, that you need to have a baseline system in order to do this. That said, there are ways to do it without a baseline translation system. You can use a dictionary. There's entire areas of work on how to do parallel corpus mining bootstrapped. But for our EU language case, fortunately, the European Parliament has translated enough text that we can build a reasonable translation system for all of the languages that we're covering in the project. And it needs to be fast. Some indicative numbers, I've burned $1.2 million in Microsoft Azure credits. I didn't actually pay for them, but they were donated by Microsoft through the Alan Turing Institute, thank you. And that still wasn't enough, actually. So we're getting supercomputer time, hopefully in Edinburgh and possibly in Cambridge, to burn a few more million hours of GPU time to do this. But if we can make translation faster, we can process more of the web and then find more data. So that's why there's a second part of the talk after this. Right. So another problem is if we go to a bank or something, it's got this giant disclaimer at the bottom, Santander, and it says, we have this address, you can register here, and actually that disclaimer at the bottom can be longer than the rest of the text on the page. So if you're trying to match pages based on their content, you're going to match on the disclaimer, do a very good job at translating that disclaimer, but you're not going to get any of the unique content that exists on the rest of the pages. If you are specifically targeting one site to crawl, this is fairly easy. You can just look at the disclaimers manually and throw them out. At scale, when you're crawling 500,000 websites, that doesn't really work anymore. We don't have a great solution to this, I'd say. It's still an ongoing thing. Like, crawling the web is kind of like window manager customization. It never ends how you can customize it and make it better in little ways. So we're running boilerplate detection with boiler pipe. But it's not perfect, and we do lose some data through that process. Another problem we have is Booking.com. So Booking.com uses a lot of templates to generate sentences, and that means you get these good translations that are relatively boring. There's only so many ways you can say that this hotel is this far away from some exciting place, and if the only thing different in the sentence is some number, then the translation system isn't really going to learn much from that. So we've actually added to the pipeline, you do hashing of n-grams and throw some hash code out. You can also use SimHash. I don't know if you've heard of it, but it tries to detect similar pages. And then we attempt to throw out similar sentences and only produce a few copies of them in the final corpus. The other fun thing about Booking.com is the reviews are often machine translated. So we might be ingesting machine translations that came out of Booking.com, and that's a problem actually on a lot of websites. That there is work on finding translations from the content. However, it mostly worked for older style statistical MT models, and the neural ones, there's a lot less work on identifying translations, but it's still worthwhile to run the statistical stuff to throw out bad translations from statistical MT. Here's some indicator of how much noise is in it at this stage of the pipeline. We took some English-German translations and paid people to annotate, I believe, 2,000 sentence pairs about how they felt about, is this a parallel language? And you can see actually coming out of this messy pipeline that does approximate string matching, it's pretty noisy. There's a lot of sentences that aren't translations. Actually, almost half of them, 41%, are not translations. Or you get things that are sort of translations, like it's English on both sides, but it's not German on one side, and that could be bad because then we're training our system to just copy German to German instead of actually translating if we throw that into the corpus. Also, non-linguistic characters is an interesting category. We're not really sure what to do with strings of emojis right now, but they're in our corpus. So we try and clean it. There's a classifier. It's some scikit-learn-based stuff. I wouldn't describe it as the most exciting neural network model of all time, but it's trained on 50,000 good parallel sentences where we use some clean data that already exists and bureaucrats or other people have cleaned for us. Then we throw in bad sentences. These can be either ones that we've found in the corpus crawl, or we just damage sentences and shuffle them, that sort of thing, to produce bad examples. And Google actually had a nice paper about how to produce good negative examples for training such a classifier. There's also a lot of handwritten rules, if I'm honest. This is inevitably, sometimes you just end up writing rules that target very popular behaviors that are breaking it. We have a particular problem right now with menus in web pages, where the system's extracting each item in the menu and concatenating them together, so you get this nonsense, what should be bulleted point thing, and it's a translation of the other menu, in the same order, so that's kind of okay, but it's not actually a sentence. And we're trying to fix that right now with a word-based language model. So currently it runs a character model that's partly to detect weird character strings and misspellings and that sort of thing. And also to ensure that we have the correct language, that it's in good Unicode, which is still a problem no matter how much you try and clean the data. You can never be sure it's really in UTF-8. And the other fun thing, though, is there's a lot of different corpora available for various languages, especially when you're operating for 26 to 29 of them. So we're not sure how to set the thresholds for this classifier, because for Maltese, you probably want as much data as you can get, even if it's kind of noisy. But for some other languages, you might want to have cleaner data because you have a lot of clean data to begin with. And there's a lot of experimentation to be done about where do we set the thresholds, how much do we clean, how aggressive, that sort of thing. And it's probably language dependent. And honestly, if someone releases another corpus, maybe ours should become cleaner once that clean corpus exists as part of the baseline. So we're trying to be consistent across languages, but I'm not sure that's the optimal thing. And it's actually a hard problem to optimize where that threshold should be. So one thing we did is when you have a problem, outsource it to the community and run a shared task on corpus filtering. And there were several interesting papers that came in. One of them was a lot more aggressive language model filtering to ensure that things are in the appropriate language. Then there was this interesting submission from Microsoft where they took a machine translation system and scored it in both directions. So they took a French-English system and well, sorry, I should say German in this case. It was run on German. So they took a German-English and an English-German system and scored the candidate sentences in both directions. And if the scores were both good and near each other, then it ranked highly. That near each other criterion is quite interesting because it suggests that maybe a machine translation is characterized by a high score in one direction and a low score in the other direction. Just a hypothesis there. We've been implementing this, but the fun thing is we ran this in 2018 on German with very high resource language. And then next year, Philip Kuhn ran the task on Nepali and Sinhala, low resource languages. And the technique that won, this thing from Microsoft last year, was replicated by almost everyone the next year for those low resource languages, and they all did bad on that. So it actually depends on how high resource language you're working with, what filtering technique you should use. Then we had some fun with copyright. This is a crawling project after all. I have no idea how Ukrainian copyright law works, but we are collecting from a bunch of websites. We are not emailing them to ask permission. We're just going to their robots.txt, as is the custom of my people, and downloading sites that allow us to crawl with their robots.txt. So we put in the user agent, here's our contact information on the website. There's a takedown thing, that email goes to me. And actually, we've had very few takedown requests. Like a few people have emailed mostly saying, could you stop crawling our website, please? And okay, fair enough. Also in Europe, there's privacy laws that have gone into effect. And then this has nasty interactions with anonymization. So should we anonymize our corpus by just moving people's names around so they're dissociated from the sentence, but then they might end up in a sentence that wasn't on the internet and could be libelous about them because we've been anonymizing and moving personal names around? Also, they have the right to correct their information. Honestly, that would be kind of cool if someone sent us, here's a better translation. But generally, our attitude is okay, contact us. We'll remove everything from the crawl. It's one website out of 500,000. For Irish, it'd be kind of bad because like one website is most of the data, but for the other languages, we're mostly fine. And this actually blew up a bit because there's this company, the European Language Resource Association, that's part of this consortium. And he literally said the first word of copyright is copy, and you're copying data, and that's a problem. So I went to his website and I found them selling someone else's crawled parallel corpus, and then he took it down. And that's where our detente is currently settled. This is the end of the parallel corpus crawling bit. There's, of course, lots of corpora out there that are open, and people put effort into that, and I appreciate that. European Parliament is particularly famous, but there's a lot on Opus, and someone went and collected all the Jehovah's Witnesses data for a variety of languages, and now there's a lot of low resource languages where as long as you're willing to tolerate interesting religious content from the Jehovah's Witnesses, you can build translation systems for low resource languages. And this project is not necessarily new per se. Web companies have been doing it forever, or at least since 2010. And the real difference here is that it's open, and it's time that research groups be able to compete with large search engines in terms of the amount of data that they have available to train their systems. But Google can use it too. It's Creative Commons 0. So moving on to browser translation, which is partly motivated in this talk by the need to translate things fast. This is a collaboration with Charles University, University of Tartu, Sheffield, and Mozilla, and I'm the coordinator of this project. And there's the legally required disclaimer about our funding. So, motivation for this project is in Norway, the state oil company put a lot of their documents through translate.com, which in fairness has a policy that actually says, we will post the data you put into translate.com for the community to see, but apparently they didn't read the policy, so a bunch of confidential information leaked on translate.com. That's a problem. So another way of putting it is Google gets the data when you send it to Translate, or translate.com does. And so we wanted to do client-side translation, and we partnered with Mozilla to do this in Firefox, partly because they don't have the feature right now. You get an interface that looks a bit like this. If you speak English, so you use your interface language is in English, and it detects that the language is in a different one. This pops up at the top of the screen, and it offers to translate it. That's at least the user interface design, and it should all run locally on your machine. That's the idea. And actually, we're going further than just translation inside of Firefox. We're trying to expose quality estimates to people and show them to the user, because there's problems now that neural machine translation is really fluent, but it doesn't necessarily mean the same thing as the input. And that's an issue, because there's research showing that people out of UMD studied and showed them fluent translations that were wrong, and they trusted those more than the disfluent translations that at least were accurate to the source. It makes sense. If your only guide is that, then fluency is a good thing to look at. But if we can show the user something else, that's helpful. And there's some other interesting features, and this is roughly an outline of features I will go through. So I don't know if you've been involved in European Union projects, but we're making a public product, not some demo, and we actually want it to be usable. So I've actually brought in some user experience people, their work package 1 on this, to do proper studies of usability of this interface, especially for the new things like showing quality estimates to people. How tolerant are they of how long it takes to translate versus what should the quality be? That sort of question we're wrestling with in the project. We also got some unexpected press attention. So ZDNet put this article up. They found our project website, Firefox to get page translation feature like Chrome. We also got Ukrainian press. Hi. More Ukrainian press. Hopefully this says something good about the project. Okay, and the language classifier appears to be working in this case, good. Okay, so we want this to run on your desktop. And your desktop may or may not have a GPU. Well, it probably has something to show on a monitor, but maybe not a powerful GPU that could run translation well. And the CPU is the natural place to run this. So I've partnered actually with Microsoft, who hired the original developer of Marian, which is a toolkit we use, and partnered with Intel to make a faster translation that runs inference on a desktop CPU. And there's this speed contest run by the Workshop on Neural Generation and Translation. Along with Microsoft, we participated in that. And you can see this weird graph here. So on the y-axis is quality, higher is better. And then on the x-axis is how many million words can you translate for $1 on Amazon, based on the prices that AWS charges for a GPU and a CPU. That's just a heuristic we're using to put CPU and GPU on the same plot, really. It's just the scaling factor. And the fact that the CPU and GPU are relatively close on this plot, the blue and the red line are somewhat close, is largely Amazon did a good job of pricing at compute power. That doesn't actually necessarily mean something about the relative power of the two. In case you're wondering, the CPU is a Skylake Xeon processor. We'll get into way too much detail about what that means soon. And the GPU is a V100. In 2018, we had these submissions. It was the same task. And then in 2019, they got about 5 times faster. And also, you can see there's this curve. It's not just a single point. And the reason for that is there's a number of approximations and model size changes you can make that trade between the quality of the model and the amount of time it takes to translate. And that's partly what we're trying to figure out. Where should we exist in this trade-off in order to make it a usable product for Firefox people? Should we sacrifice some quality? Do we translate things at the top of the page first and then just in the background more aggressively do a good job at the other parts of the page? Those sorts of ideas we're throwing around right now in our project. So I'm going to talk about some of the optimizations, not all of them, in order to achieve this. We can obviously tune the size of the model, but that's not terribly interesting. It's just something you should do. And then I'll talk through each of these points about things we did in collaboration with Microsoft to make performance better. The first one is teacher-student training. This is not a new idea, Kim and Rush 2016. The idea, though, is you train a high-quality translation system, a really expensive one, and then you use that to translate data in your source language to the target language. So now you have a corpus of legitimate source language text and kind of weird translation output in the target language. And what that does is, in a sense, smooth out the data. It makes it look more regular. It makes it look more like something a neural network can understand. That's at least the theory of it. And then you train this student model on that corpus. Now, neural networks tend to increase biases in training data. So if there's a choice of using either of 2 words, it's going to pick one of them typically, because that's partly the training objective does that. And if you train a neural network and then train another one on its output, that's going to amplify the bias even more. And there's actually a fair amount of work on gender bias in translation. And if you enter a stereotypical female job, does it use a female pronoun, those sorts of things, which we really need to investigate in the context of this. We haven't done a proper study on it yet. But I'm showing you, at least in terms of blue scores, which we can argue about whether they're the best evaluation of translation quality, the amount of time it takes on a GPU, in this case, this is the number of seconds to translate 2,797 sentences on that V100 GPU. And if we have an ensemble of 4 teachers with a beam size of 8, it takes 410 seconds, but then we can actually compress it to an even smaller system that runs faster, and you can take an ensemble and still get some of the gains from an ensemble even though you're only running one student. Another thing that was sort of on the previous slide is this notion that because biases are amplified, actually students are very opinionated about what they think the next word should be. And that means it's not really worth doing a proper search across multiple different translations. You might run some sort of beam search procedure and then hope that the score of one translation could change and it could go up, and maybe the words in the future will move things around. But in practice, just following greedy, pick the highest scoring next word, pick the highest scoring next word as you generate a sentence from left to right, works almost as well as doing a proper search procedure when you're in a student. And that's partly because it's not really going to choose alternative words, it's picking one of them that was regularized out by the teacher. And then when we run with beam size 1, it gets faster, and it actually gets somewhat superlinearly faster. And the reason for that is when you're running in beam size 1, you don't have to normalize probabilities anymore. You just pick the highest thing coming out of the softmax layer in an output matrix for a neural network and follow that one. And there's no need to normalize because you're never going to compare scores with each other anyway. Another thing we did was take a paper from this guy, Biao Zhang. And in a transformer model, you generate a sentence from left to right typically. And each time it generates a word, it looks at all the prior words that it's generated. It does this attention mechanism to things, if you've heard of that. But looking at all of those prior words costs the number of prior words that exist in the currently generated translation. And if you sum all that up, it's an O of n squared algorithm to generate a sentence in this translation system. But he came up with a relatively simple idea, which is just average. Instead of doing some fancy weighting of all the prior states, just compute the average, and that works just as well. And then you can compute a rolling average of all of the prior words that you've generated on the fly with a minor update rule of the average, and that runs in linear time in the length of the sentence. You can see no change in quality, but it goes a lot faster on the GPU to fewer seconds. And actually in the 2019 submission, we went even further, and there was the simple recurrent unit, and then someone simplified it more, so it became the simplified simple recurrent unit, the SSRU, which we ran in the 2019 submission, but I'm not going to cover that. Another thing that is actually one of my favorites is integer arithmetic and quantization. This is a fairly common trick in the vision field, and it's increasingly popular in natural language processing these days. So we did some performance measurements, benchmarking on CPUs and GPUs, and saw that memory bandwidth was a blocker. If you look at a Volta GPU, it has those tensor cores that are really fast at crunching numbers, but it doesn't have the memory bandwidth to support feeding those tensor cores all the time. So if you can compress your model, get more numbers in, smaller model, less memory bandwidth usage and go faster. And actually, there's some work showing that you can do 8-bit integer arithmetic for machine translation, and there's no quality loss, and as long as you're careful about fitting scaling factors and such. But how do you actually implement 8-bit matrix multiplication on a CPU? There's one instruction, and this is my rant to Intel, where if you're coding in C, it's madd ubs, and then if it's in assembly, it's vector packed multiply add unsigned by signed wide. That's yes, and it's the only instruction that does an 8-bit integer multiply, which is the basic operation if you're doing matrix multiplication in a neural network with 8-bit integers. And it's unsigned times signed integer. And I've been pressing Intel on this. Why is it signed times unsigned? And I haven't gotten a great answer out of them. And also, even their new instruction, this VNNI thing, which is vector neural network native, is signed times unsigned. So something specifically designed to make neural networks go fast wants one of the arguments to be a signed 8-bit and the other one to be an unsigned 8-bit. I bet you weren't expecting assembly code in this talk. So how do we work around this? There's two methods. One of them is you can add 128 to one of your arguments, and then it's no longer a signed argument. It's just an unsigned integer. And this is actually what TensorFlow does, and MKLDNN implement this one. And it's efficient if one of the arguments to your multiply is constant. I only worked it out for A, but you can work it out for B. And then in the case of inference, one of the arguments is constant. It's the parameter matrix. So you can actually pre-compute what the offsets are for this. There's a subtlety, though, that this accumulates in a 16-bit integer, and having some big number like 128 increases your risk of overflow. Fun fact. So actually, it can be less accurate to run the skew method. The other one is to normalize the sign bit. So you just manually run a few instructions that take the negative or positive sign off of one of your arguments and multiply it into the other one in advance of this 8-bit multiply. And we actually implement both of them in this open source library I've got to do 8-bit matrix multiplication. But this is more of a rant about how you have to work around weird architectural things that were probably not designed for 8-bit matrix multiplication. And then we ask the question, okay, we've done 8 bits. And there's prior work showing you don't lose quality. Can we go down to 4 bits? And 4 bits is nice because it's electronically convenient. You don't want to have 5 bits. It's kind of ugly to have in registers or something. So we ran a sweep. Just, by the way, this is an emulation experiment. We didn't actually implement a 5-bit multiplication kernel. We cheated a little bit and quantized things down to 5 bits and put them back into floats, and then emulated what the instructions would look like. And we swept how much quality you get. So these numbers in green and red are the translation quality. At 8-bit, you get pretty great. And for some reason, with 7-bit, you get slightly better, but insignificantly better quality. But then, annoyingly, right at 4 bits, it really drops off and becomes not so great translation. So if we could just squeeze a little bit more out of this, then we might improve things. And I should also note here that we're quantizing the log. We're not doing fixed point quantization. And there's a reason for this. In a neural network, most of the parameters are near 0. So to minimize encoding error for most of the parameters, you want to encode the log because that has a lot more precision near 0 than it does for larger values. And the other thing is larger values are generally just large, and they're probably going to win anyway if they're large. So it's not as important to encode those large values as long as you represent them in some way. You can't just clip them. That damages quality, but if you approximate them, it's kind of okay. And this is based on some vision work that was done previously by that cited author. So then in order to squeeze things into 4 bits, we tried a bit harder. Previously, we were just taking the model as trained, quantizing it, and then trying to get performance out of it. But then we went back to the old trick. This is not necessarily new, of retraining the model. So you take a fully trained translation system using floats as normal, and then start damaging it with this quantization thing. And you run continued training, so you just carry on training the model, but every single time it updates the parameters, you force those parameters back into 4-bit integers. And there's an important trick that we got from Microsoft and Frank Side, where you can't just forget those rounding errors when you quantize, because any small change that comes from a gradient is never going to be able to flip the parameter to the next quantization point. So you remember the rounding error when you quantize, and you add it to the next gradient and just carry the error forward. It's kind of like having extra precision in the parameters that are only used for updating them, but not for running the forward or backward passes. And with that, we were able to get a relatively small degradation in translation quality, minus 0.19, so wouldn't be publishable if it was a gain, which is good, I guess. And see our archive paper, it's not actually properly published at this point, but this was with my student Elham Fikriaji, who you should hire. Then we have another project just to make things go fast. Linguists like violent examples, so we thought we would follow in the tradition. Transformer models for machine translation have these heads, and there's a lot of them. So a typical translation model has 6 layers, and it does self-attention, which is this thing where it's looking at all the other words that are in the input sentence. And then in the decoder that produces the output sentence, it has both the self-attention where it looks back at all the words it's produced, that was the O of n squared thing before, and it also has these heads that look at the input sentence. And by default, in a normal stock configuration, you might have 6 layers, 8 of each type of head, and that's a total of 144 heads. So the question is, can we decapitate some of these and still have good performance? Lena Voida, who's actually joint between Yenex and Amsterdam and Edinburgh somehow, put a paper out where after training, she said you can prune about half the heads, they just don't do very much. But she then tried taking the network structure that she had pruned and reinitializing it and starting again, so maybe it's just a better network structure that she discovered, but that didn't work. You get lower quality if you reinitialize the same network structure and then try and train it. So my PhD student, Maxi, had a different idea at cheating this. What if we pruned during training? It's not quite at the beginning and it's not quite at the end. And we've been working on investigating that idea along with the lottery ticket hypothesis. Don't know if you're familiar with this, but it's this idea that in a neural network, there is a lot of garbage. Most of the parameters aren't doing anything, but if you try and reduce the parameters up front, then actually what's happening is every parameter is some entry into a lottery, and the number of parameters is buying that many lottery tickets, and some of the parameters will fit well. However, it was initialized, it might be a great parameter. So this is the idea that training a large model is actually benefiting from more entries rather than actually using all of the capacity of the model. And typically this sort of pruning in the lottery ticket hypothesis, when it's productionized to make models go faster, is done at the coefficient level. So you might make a sparse matrix out of it. But the problem with these sparse matrices is unless you're well over 80% sparse, it's not going to go faster on a CPU. The hardware just isn't capable of dealing with sparse matrices in an efficient way at that level of sparsity. But block sparsity is nice because you can remove an entire head and then you just don't have to run it at all. You can remove it from the model. So the question we asked is really, can we duct tape this lottery ticket hypothesis thing to Lena Voita's paper where she said you can throw out 50%, and maybe we can decapitate even more heads. We did that, and this is a preliminary result where in this table I'm showing at the top line how many of the heads we pruned from the model, starting with 0 as the baseline, and then 55, 72%, 83%. And this 83% is right around where it starts causing a lot of damage to the model, that minus 0.93 blue. We ran it over a few test sets and recorded how much we were losing relative to the baseline. So the reason you see a dash in the leftmost column is that's what we're measuring relative to. And also we measured the speed up by, if we remove these heads, how much faster does it go in an actual translation model? And we're getting somewhat reasonable speed up, so 1.53x for a 0.2 blue loss. And this is going to create yet another trade-off between quality and speed that we can add to that Pareto curve we're trying to get. And we're still working on it in the sense that we should prove that this is Pareto optimal with respect to all the other optimizations. The size reduction is actually not that big, and the reason for that is most of the parameters aren't found in heads. Most of the parameters in a natural language processing model are word embeddings, and we weren't touching the word embeddings at all. But these heads get used a lot. Word embeddings tend to only be used when the word appears in the input sentence or when the word appears, is likely in the output sentence. Moving on, I mentioned this earlier that we wanted to do quality estimation. So this is the idea that the translation system might make a mistake, and ideally we could alert people to the translation system having some sort of error. And the example of this is the Israeli police used Facebook to translate a post by a Palestinian, and he had said good morning in Arabic, and somehow Facebook translated it to attack them. The Israeli police saw this, and they never consulted an Arabic speaker to actually read the original sentence. And this construction worker guy he was on a construction site with heavy equipment that looked like he might be able to attack people. Yeah, so not so great occurrence, but it happened, and it shows there's a problem. And also, somewhat disturbingly, the Department of Homeland Security in the United States gives instructions to their officers on vetting social media, and they include click-by-click instructions on how to copy-paste people's tweets into Google Translate. But there aren't any instructions on how to actually validate any of their suspicions. So a visa could be denied to someone on the basis of a translation error. We're creating somewhat scary technology, or helping governments bomb people more accurately if they mistranslate something, though I hope they would actually consult a human in that case. So we want to show quality estimates to the user, and that's difficult because you need to have a user interface that's unobtrusive. If it's a good translation, maybe we should say nothing. And there's actually an even worse risk that what if our translation is bad and our quality estimates are also bad, and it tells the user it was a good translation? Are we going to make the Israeli police even more aggressive? That's a problem. So maybe we'll only show bad quality estimates or some document level estimates. That's what we're struggling with in our user experience research right now and recruiting participants for. The other use case we have is, I was in Denmark for a conference and had these old Danish bus tickets. They're no longer in use, but you can get a refund for them if you file an online form in Danish. I don't speak Danish, But I need to produce some answers in Danish to this form. And we have a project that's in a browser, so we want some feature that will help me do this. In practice, what I did was I gave the train ticket to Dirk Hovey, don't know if you know him, and he gave me a beer back, and I don't know if he actually filed for the reimbursement. But what if we don't have Dirk Hovey? Then we want some way to answer this Danish web form in Danish. And the idea is we can use quality estimation. If we're not confident about our translation from English to Danish in this example, then maybe the browser can come back to me and say, could you rephrase your input? And then we have the question that the form is asking with some approximation of was it actually the question, and an input from the user and another input from the user if they rephrase it. And then we hope to triangulate a better translation into Danish in that case. So getting close to the end of the talk here, the other thing is we're in the browser and we're trying to figure out how creepy one can be about this. But the browser history is a thing. And if you know that someone looks at bureaucratic sites, can we translate the chair into La Présidente for that bureaucrat who's looking at those sites, and otherwise translate it in the consumer meaning? Do some domain adaptation based on the browser's user history. And actually, we can do this better because we're in the browser and have history, and in theory, at least, Google should not have access to your browser history. And so we want to adapt the translations to both the user and the page that they're specifically on, and that actually ties into some of the web crawling stuff. We might know in advance that if you're on that web domain, it tends to be this sort of genre. Yeah, hopefully less creepy when all processing is local. This is more of a product decision, honestly, about whether this gets integrated or not. But at least we could do domain adaptation on the page that you're seeing. I think that's within a user's expectations. So to summarize, we're doing a privacy-preserving translation, targeting corporate users, government users, and people who want to preserve their privacy at home, hopefully coming as a Firefox extension. We do not have Ukrainian in there, but hi. And I can actually show you a 30-second demo of this, which is what the media found. So this is German Mozilla site. And he's just scrolling through it to show you that there's a lot of German. And it's brought up this translation thing. He clicks that. It sends it to some translation that we're running, and then it comes out in English.